So one of the things I want to point out here is this really just isn't one of those things that you can just skip and kind of ignore and it's going to be okay. Okay? You really got to, there's a combination of memorization and immersion in learning this new language. That's the language of science that you're just going to have to do. Okay? Because if you don't learn the language right, then when I ask you questions in that language, you're going to be very, very confused. And I'm going to have to use that language in these subsequent chapters as we go on. Okay, so I'm going to have to say things like this methyl does this, or this hydroxyl here is going to get attacked. Or I'm going to say things like, hey, the sugar has these functional groups on it. And then if you don't know what the functional groups are, then everything else doesn't make sense, does it? Okay? And so there's kind of three major parts of this course. There's the conceptual portions that are like, this is what temperature means, okay? This is what phase change means, right? And this is how those work. But then there's the language portion, right? And without the language portion, it's going to be like taking every exam in Greek or Chinese, right? A language you don't know, whatever language you don't. And then that's just not doable. It doesn't matter how good you are at the other parts. If you don't know the language, you can't do anything, can you? Okay? So please make sure that you don't just like pass. You don't do that, okay? Make sure that you study this material, do the homeworks, immerse yourself, learn that material, okay? Okay. All right, so what we're going to have here is this is that naming of the organic compounds here. Specifically, we're going to be starting with alkanes. And alkanes is like me saying alk means I don't want to count. I just want to do a generic whatever number I want to deal with, okay? So I'm not specifying the number. The ane portion means that it just has single carbon-carbon bonds, okay? Now, whenever we're talking about these organic compounds, those carbons are going to be your skeletons for these compounds, right? And they give you your structure. What we're going to then have is we're going to have the features. Those features are going to be our suffixes, or another way of saying that is our functional groups. They're going to be the important parts that's going to give us our functions, okay? Kind of like your head is a feature of you, right? You get your skeleton, but then you got a lot more important stuff in there, don't you? Okay? And those are going to be the suffix functional groups that we're going to talk about. When we're looking at organic molecules, we'll have hydrogens. The hydrogens are really just not that important, are they? Okay? They kind of just spread everywhere and fill in everything that we don't fill in with other stuff. All right. So, the nomenclature or naming rules were established by the International Union of Pure Applied Chemistry. This is IUPAC. There's kind of a funny thing where my advisor did not like these people, and they're kind of childish sometimes, and sometimes they make some very, very strange decisions that make things much harder. Okay? But I kind of get why they do that. So if you have a complete naming system, it becomes very complex, right? And so if you actually were to look this up and go into the IUPAC's website, they have a freely published set of rules. And it's a lot like, has anybody ever seen like legal documents? And so if you ever go on to like sign up for an app and you go, yes, you probably just click yes. As I found out from my last class, actually. But if you ever access that to actually look, it's this long, like addendum 1, addendum 2, addendum 3, and then they have go back to addendum 1.a, and this references that. And it looks just like that. It's several hundred pages with additional addendums that are published every year or two. And so, yeah, it is very complex, very long. I'm going to give you a summary of this that I've tried to decomplexify. Okay? And it'll be decomplexified enough. You'll be okay. I've taught hundreds of students this who have successfully passed standardized exams and all sorts of stuff. So you'll be fine. Just got to put in a little bit of practice, a little bit of work. Okay. So my advisor specifically hated them, and he was an old school chemist, and I was here before them. They can go fuck off. And they'd go, you have to use IUPAC for your publication. And he'd go, bleep, bleep, bleep. You can go shove this where you're. And he was quite a character. And the funny part is, he was an important enough scientist that he got away with it for all these years. Yeah, 1,100 publications. So, anyways, that's IUPAC naming. This is the naming language we're going to learn, okay? And what's going to happen is I'm going to start here and I'm going to make my way through, okay? Because what you're going to see is each of these things sort of modifies your names, right? So I'm going to start with parent name, and this is typically the longest continuous chain of carbons. That's going to give you your parent, okay? Now, having said that, in terms of importance, it's actually the suffix that's the most important. This is going to be your most important functional group, okay? And this most important functional group can actually override your parent name in terms of what your parent is, okay? So if your most important functional group is attached to a shorter chain, that one takes precedent, right? It's just more important because the functional groups are the things that function. They do stuff, right? So it'd be like your arm gets cut off. Yeah, it might be longer than what's left, but part with your head and your heart is more important, isn't it? Okay. Okay. And so, you take the part with the head and the heart, even though it's not as long, and you go rush that to the hospital, don't you? You don't rush the arm to the hospital and forget all the other stuff. So again, it's in terms of importance, right? So we're going to look at the functional group, the suffix. That's always going to be our primary importance, okay? And then that's going to help dictate our parent name. All things being equal, the parent name is going to be your longest carbon chain, your longest continuous carbon chain. Now, in terms of importance, your substituents are going to be your least important stuff, okay? They're literally just going to be this like long series in some of these of names that you're modifying stuff, okay? And it's kind of like when you add different adjectives, you can just sort of modify that structure, right? With those different adjectives. In this case, the substituents. The substituents literally means that substituting for a hydrogen, that we've replaced a hydrogen with this. Okay? So tells you how important those are in the grand scheme here. Now, when we're talking about branch chain alkanes, so what we're going to have here is we have an alkane. Okay? That means we have carbon-carbon single bonds and some sort of chain. Okay? I'm going to go ahead and write a structure up here. I'm going to kind of use it as a little demo and example every time I talk about this. Okay? And so, and that. Okay. And so that one right there is a branch-chained alkane. Okay? And I very specifically wrote it in a way where it's kind of reverse what you would have expected. Okay? So when I'm counting my longest continuous chain of carbons, okay, I'm going to go 1, 2, 3, 4, 5, 6, 7. And so I counted 7 carbons. Okay? Nope. Nope. Okay. I have a rule for the 6, 7. It actually has to be funny as a standalone thing if you use 6, 7 in my class. Otherwise, I'm going to be just disappointed in you. And I'm going to go, yeah.
Oh, we can barely see the drawing.
Oh, okay. Thank you for letting me know. Yeah, I'll draw one at the bottom instead then. Better?
Yeah.
Okay. Let me know if you can't see that at all. Anybody? Okay, so this one right here, when we're counting, we're going to try to count the longest continuous chain. And so 1, 2, 3, 4, 5, 6, 7, 8. Okay? So it's going to be 8 carbons is our longest continuous chain. Now, notice I did not go 1, 2, 3, 4, 5, 6, 7, 8, 9, right? That would not be continuous, would it? Those are not connected directly, are they? Okay. That'd be like taking a chain that you have another chain tied to and being like, well, it's a 10-foot chain. I can reach 10 feet, right? No, it's a 8-foot chain with 2 feet off of the side, right? You can't reach 10 feet, can you? Okay. And so you got to count the longest continuous chain. Okay. Be careful about that. It's a common mistake people make. Okay. Okay. And so the next part is we're going to identify the groups that are bonded to the main chain but not included in the main chain. That's this, isn't it? That's what we're talking about right there. And these are going to be our substituents. So that right there is I'm going to say it wrong first so you understand the connection. Okay? Everybody ready? Alkane substituent. When it's a substituent, though, we call it an alkyl substituent. Okay? And alkyl means it's a substituent. The main chain would be the alkane. Okay? In this case, we have 8, so that's octane. Oct being 8. Ane meaning we only have single bonds. Okay? This substituent right here is only 1 carbon up there, isn't it? And so 1 carbon is meth. And because it's a substituent, we go methyl. Okay? By the way, what do you think meth, the drug, is named after? Yep, methamphetamine. So it's an amphetamine with a methyl. There's a methyl that if you synthesize it on the wrong side, it's not bioactive. And so methamphetamine. Okay. And so, again, any length of that substituent, you're just going to change that ending. Instead of ane, it's going to be ill. Okay? Methyl, ethyl, propyl. You get the idea. All right. So the next thing we're going to do here is the number of carbons on the parent chain starting at the end nearest the substituent. We need to number those carbons so we can figure out where is that substituent, where is that located on our structure. Okay? Kind of like if you go up to the floors, the numbering on the beginning of the numbers of the rooms is the 3, right? So it's 300s. But then we have 301, 302, 303, right? And so we're specifying where that is along the chain of our rooms, right? Same sort of thing. If you do this in a way that actually makes sense, you would specify it in a way such as like, I don't know, I would put 301 next to the stairwell where you start, right? Apparently, whoever did this building does not agree with me. Or there was a more structural change in the building than I thought. But IUPAC agrees with me. So IUPAC, it's actually a logical place we start. Remember, again, this is a chain, right? When we're looking at a chain, it can be up and down and sideways and coiled. It doesn't matter, right? It can be all sorts of structures. Where we start is one end of the chain, right? And so, in this case, what we're going to do is if we started over here, it'd be 1, 2, 3, 4, 5, 6 until we get to the substrate, right? Over here, it's 1, 2, 3. See that? And so we get a smaller number for starting from this side. So again, there's no rule saying you have to start on the left side of a molecule. That doesn't exist. Molecules don't have a left side. They have spinning around in space. Okay? Mm-hmm.
How do you get 3?
1 carbon, 2 carbons, 3 carbons.
So wait, there's 2 on the line that's on the far right.
Mm-hmm. Yep. Anywhere the line ends. So every line is a bond. Anywhere that line ends then has to be the carbon. Okay? Unless you have something like an oxygen, chlorine, or something. Mids. Yep. And so this would be 1 here, 2 here, 3 there. Okay. Okay, so that would be 1. Mm-hmm.
Wait, so like we start from the side that.
Yep, you got it. Yeah, always give the smallest possible number to your substituents. Okay? So in this case, you'd want to start numbering from 1, 2, 3, this side over here.
So with the name you have to try it?
No. Because it's 1, 2, 3, 4, 5, 6, 7, 8 for the longest continuous chain, isn't it? So it's still going to be octane. It's just where this is located is going to be the 3rd carbon. Because it could have been located here, right? That'd be the fourth carbon. Okay. And so, you could be in different locations. Kind of like doing a different room, right? 301 here. Come to this for lab. You're going to be a little bit disappointed, aren't you? 302. Okay. Now, this one right here, this is a methyl again. And so the name for this would end up being 3-methyl and then octane. Okay. So that's because this is the substituent. It goes first. You put the number in front of that substituent, and that gives you its location. Okay, so you're going to assign a number to each substituent based on that location, listing the substituents in alphabetical order at the beginning of your name. You're going to separate any numbers and words by the name by dashes. So anywhere where you'd have a number go to a word or a word go to a number, you put a dash. Okay. You'll recognize it from like files whenever you have computers. Yeah, it's the same sort of terminology. And so if you have more than one of the same type of substituent, you don't go methyl, 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 methyl. What you do is you do a prefix in front of it. So if you had 2 methyls, it would be dimethyl. 3 methyls, trimethyl. And then you just put the number for each before it. So if we had like a 2, 3, 4, it would be 2, 3, 4, 4 dash, trimethyl. Okay? And so you'd have the tri for the number of methyls, and you'd have each location as their number. Those numbers, by the way, are called locant numbers, in case you're curious. Okay? Literally locator numbers. All right. So whenever you do this, in terms of the numberings, you always need to minimize the numbering as you go along. So your first one you number, give it the smallest number possible. The second one, if there's choices that would give you that first number the same number, give the second number the smallest number you can. Okay? And just keep going like that until you no longer have any choice. Okay. And so, again, this is a thing that practice is very much going to be helpful here, okay? You won't truly understand it until you practice. Just like you wouldn't be able to speak any lick of Spanish until you practice it, right? You actually get immersed in it and speak it, okay? You think you maybe can, you can't. You can't go to Mexico or anywhere Spanish, and they're going to go, what the hell are you saying? Okay. These right here are the different Lewis structures, the condensed structure, the line structure, and finally the ball stick structure for our different substituents we just talked about. Right here's our methyl, ethyl, this is propyl. Now this one right here is called isopropyl. So the iso is this right here where it has the 2 methyls off the tip right there. See that? And propyl means 3. So it is that restructured 3 carbons, okay? Where it has this structure right here. See, it's 3 carbons. You're attached in the middle here to your longest chain, your parent, okay? Okay, now, this right here where you have the wiggly line, that's that connection to your parent chain, okay? So there could be an octane over here. We just don't care right now. We're just trying to get the parent chain. We're trying to get the substituents figured out right now. Okay. By the way, in case you're wondering, isopropyl alcohol, rubbing alcohol, that is this same structure right here. There's just an alcohol over here instead of a chain. Okay. Now, halogens, these are going to be a very common substituent on alkane chains. These will be called haloalkanes or alkyl halides. And halogens, again, are that 7th group right up there that's next to the noble gases. They always want to make one bond, right? And so this is one of the reasons why they're such common substituents. Literally, they just end up substituting for hydrogens, don't they? Because they only make one bond, okay? They don't change the structure much. So they're always going to be substituents. They're never going to be your functional group suffix. They're never that important, okay? So they're always going to act as substituents. In order from top to bottom, we have fluoro, chloro, bromo, and iodo. That would be the fluorine, chlorine, bromine, iodine. And again, for naming haloalkanes, they're going to be the same as for the naming of your branch chain alkanes. Your halogen is just going to be a substituent off of that, taking the place of a hydrogen. Okay. All right, so the cycloalkanes, cyclo meaning cyclic, right? So it's a ring. Okay. And so what you're going to have here is you're just going to have basically the same naming as before. Just keep in mind that's a ring now. Okay. So it's going to come back into itself. If you look at any ring, where's the start and where's the end? There's not really a start and end, is there? So you get to assign whatever you want, essentially. Okay? And so the ring is going to be your parent as long as it has more carbons than the substituent, as long as it has more carbons than the straight chain portion. Okay? You're going to identify the substituents. You're going to number the carbons in the ring. You'll start carbon 1 on a substituent, as long as you have one. Okay? And so the interesting thing, which is the substituent, is always going to be carbon 1. Because that's the unique, interesting feature, right? Just like if you were to start naming, like pick a point on a sphere, that's the start point, you'd always pick something interesting, right? Something meaningful to you. Okay? So number 4 is going to be assigned numbers to the substituent. On a ring bearing a single substituent, we actually don't have to do any numbering because 1 is implied. Whatever the substituent is, that's number 1. Okay? And so everybody looks at it, that's going to be number 1 because it's the only place for something interesting, right? The only place that has an obvious start point. If you have more than one substituent, though, you're going to give your lowest possible number. So you're going to go and give 1 to the first one, substituent, and then give the lowest possible number to the next substituent. Okay? You're just going to go through giving the lowest numbers you can. All right. So organic compounds with the same number of carbon atoms can have carbons connected in many different ways. Molecules with the same molecular formula, but that have different connectivity or arrangements of the atoms, are going to be called isomers. Iso means same, meros means part. And so they have part same. So you got it. And so isomers. Now, again, these are going to have the same molecular formula, but different connectivity or arrangements. So in three-dimensional space, they'll look different, or they'll just wholesale have a different connectivity. Okay? This is an example of a structural isomer. So this one is connected differently. Everybody see it okay? So here it's just a straight chain, isn't it? We have 4 carbons and 10 hydrogens, same molecular formula. We look over here and look at that. It's connected differently, isn't it? Yeah, that's going to end up with a propyl there, and that's a meth, right? Methylpropyl. And so they look quite different, don't they? And those are our structural isomers that we're talking about right now. The next one is going to be the conformational isomers down here. So these are going to have the same structure, but they look different because they can rotate freely. Okay? And so one of the things I'm going to recommend is next week we'll have model kits, and I'll break you into groups of, the 24 people in the groups, and I'll be able to take you through and do models with you, okay? And we'll assemble the models, we'll work on some naming, etc. Okay? Okay. Now, this week I'm actually going to start you off with your hands and a tactile sense and response, okay? Because how we develop as babies means that our most visceral responses are always our sense of touch and our sense of smell. I would prefer not to do sense of smell for chemicals, so we're going to avoid that right now, okay? But we can use our sense of touch to get a much more visceral, memorable response to this, okay? So please do follow along and actually use your hands. Honestly, you're going to look sillier not understanding it than you will look using your hands to do stuff, okay? Okay, so this right here is going to be conformational isomers, right? And remember, they're kind of like chains, aren't they? So if we have a chain, we can, just drop it and it'll wind up on us, right? And we can flip it over, and we're going to flip over that chain so it has a part extending, right? And so when you have all single bonds like this, these are going to be referred to as conformational isomers, where they're not actually different molecules at all. They aren't connected differently. They're not actually different in three-dimensional space in any way that is permanent. Okay? They're going to be kind of like you have in your hands here. I can be like this, right? Okay. Without breaking any bonds, though, I can go like that, can't I? And that's essentially what this has done, isn't it? It's like this right now on the leftmost. And then we went like that, didn't we? And that's what the two are. That's the only difference. Okay? They're not permanently different. They're just different arrangements of the exact same compound. Okay? And so that's normally referred to as conformers. That's how it's going to be expressed 90% of the time that you would ever hear this. Conformational isomers is very, very, very rarely used because the isomers imply. Okay, so we've got structural so far and conformational isomers, right? So I'm gonna start a flow chart in your head. Okay, you guys ready for it to burn it into your minds? Okay, so you have nightmares about it. All right. So this is going to be, do the molecules have the same molecular formula? If they don't have the same molecular formula, then they're just not even isomers, are they? They have different numbers of carbons, different number of hydrogens, there's different compounds. Okay? Not isomers at all. If they have the same molecular formula, then they're an isomer of some sort. Okay? So far, we just have the two different types of isomers. So, do the molecules have the same name? Remember that the naming actually is going to tell you where things are connected to each other, right? So if you go through and do IUPAC naming, well, guess what? They have a different name, then they're going to be structural isomers, aren't they? Okay? If they have the same name, then they have to be one of the types of isomers that has the same structure, right? So if they have the same name, so far, the only one we have that would have the same name is a conformational isomer. Okay? If they have different names, then they have to be structural isomers. Because, like I had mentioned when I got to this, those have different names, don't they? Okay. Now, the cis-trans stereoisomers and the cycloalkanes and alkenes. Okay, so you remember when I went like this, right? I only have one connecting point, don't I? And so having that one connecting point, I can rotate around it very easily, can't I? No matter how I do the one connecting point, it rotates easily, doesn't it? You can also do this with a pencil or a pen in your hands, and you'll get the exact same effects, okay? Now, what happens if I make two connecting points now? Can I rotate now without breaking them? No, even trying to, I broke it, didn't I? Yeah. So that right there would be like a cycloalkane, wouldn't it? That's a cycloalkane. If I try to rotate around this now, I break it, don't I? So what does that mean? Well, it means it has different isomers that are permanent now. Okay? That being on different sides of that ring is going to be a permanent fixture that you can't just rotate and fix, can you? Okay? Because we have the two connections. Now, when we have a double bond, you're going to experience the same thing. If we have a double bond, that's going to be the two connections again, right? And when we try to rotate it, what happens? Well, if we rotate it, we break one, don't we? Okay? See that? And not without, it wouldn't actually rotate, would it? See, they're still on the same opposite sides.
Oh.
So even if you go like this, if they're on the same side, even if you go like that, it's the same. Okay. And so we have to have a designation to tell us, hey, these things are on opposite or same sides. Okay. If they're on the same side, that's going to be cis. If they're on opposite sides, that's going to be trans. So right here we have trans. Over here we have cis. These are on the same side. See that? Both going away from you. These are on opposite sides. This is actually what this looks like in terms of this. So this one looks like that right there. Excuse me, like this. Am I the correct one? Nope, this one's right. Okay, this one's coming out towards you, right? This other one's going away from you. Okay? This other one looks like that, where they're both going away from you, right? Okay. So remember, you can actually use your hands on exams. Those are a free material that I can't limit you from having. No hands for the exam. Or confiscation when you come in. Slice. So obviously you get your hands on the exam, so you can do this for yourself. Could this rotate? Yeah, it can rotate. Oh, double bond. Nope, can't rotate, right? And you can actually use that to help you out. Okay. You'll actually see that in a lot of my classes, people doing that, getting the right answers. All right. So the next thing we're going to go on here is, remember that when we have that restricted rotation, this is going to give you something that's called a stereoisomer. Stereo meaning they're different in three-dimensional space. Okay? Same reason that stereo system has that name stereo, right? Stereo system, you can hear sound as if it was coming across your field of vision, right? So you can hear it as if it's over here versus over here. Okay. And so those are a stereo system, stereoisomers. This is just the other way of looking at this. So now I'm looking at top and bottom here, right? Versus both on the same side, top. And so again, this one right here is cis, this one is trans. Typically when I say cis or trans, though, I'm going to be talking about the most interesting things, okay? So in this case, the most interesting things, the substituents here, are going to be my methyls, okay? The hydrogens just are not interesting, we don't care. Now, you can use this language to talk about other stuff, okay? So you can say that these, my methyls are trans from each other right here. My methyls are cis from each other right here, okay? But you can also use that language to go, my hydrogens are trans to each other. My hydrogens are cis to each other, okay? And you could also use it to say, my methyl and hydrogens are trans to each other, okay? That still has meaning. It just is not as meaningful as just saying cis and then my methyls are cis to each other, okay? That would be the default. Okay, I am kind of gonna, I'll give you the thing, but I don't think anybody really needs it anymore. The cis-trans language has become very pervasive through society, so I think that everybody kind of knows cis-trans and essentially what it means. But if you don't know and you don't remember, cis, S, it sounds like S, right? So cis, same sign, okay? Trans is actually Latin for across. So trans, as in transport, right? You're crossing. Okay? So trans, cross. Now, when you use these for names, they're actually going to be included at the beginning of the name, and they'll be put in italics. Okay? You can write semi-cursive-ish, okay? If you're writing it by hand. And this is going to happen when you have a cycloalkane or an alkene. Alkene being the double bond one. Okay. Now, again, those are going to trap them on the two sides, and that's going to mean you have that permanent fixture, which is the stereoisomer. Okay. Note that these are always a modification of your substituents. It's only when you have substituents that this is really going to matter. Okay. So you have to have like carbons on the two sides or something. Okay. Now, the carbon-carbon double bond, if we're talking organic chemist language, then it's going to be rigid, or it's going to be restricted rotation. So it can no longer rotate unrestrictedly. Okay? Or another way of thinking it's rigid, right? It can only move certain ways. Okay? Now, a compound with a similar group on the same side of the double bond is going to be your cis. Compounds where the similar groups are on opposite sides are your trans. And if one of the alkene carbons has two identical groups bonded to it, you can't actually have a cis or trans. Okay? So let's go ahead and look at this again. This is your cis, right? This is your trans. Okay? If we had another methyl right there, that CH3, then you really can't be either, can you? You'd be both cis and trans. Okay? Because, yeah, you'd have a methyl on the same side here, right? But you'd have one on the opposite side as well. Okay? And so if you have the same group on both sides of one of these carbons, automatically it can't be you. You just can't be cis or trans. Okay? Because it's the same both ways. All right, so you all may have realized when you're listening to me talk about this that I have heard that somewhere before. I have heard of cis trans things. Okay? They exist other places. And that's probably from cis trans fats. Okay? That is the most likely. Who here has heard cis trans fats? Good, thank God. Thank you.
Yeah, trans fats are like really
They are. We had our time breaking them down. They also get incorporated in structures. They have different physical properties. We'll talk more on that as we go along. But they are incredibly rare in nature. Just almost unheard of in nature. Okay? In a normal human diet, before all the processing of foods, you would have never seen a trans fat into your diet. It just wouldn't have happened. So the omega, you may have heard of like omega fatty acids. So omega is this. This is the symbol for omega, in case you're wondering. This is going to be a designation commonly used in nutritional literature. Yeah, do they have like middle school health class anymore? High school, middle school, elementary school, anything? Health class? Go.
Yeah, when I was in Germany, yeah.
Okay. Yeah, they definitely have them in other countries. They used to have them here. Apparently, they don't have them here anymore, which is really disturbing. Like, did you guys know that under the previous guidelines for nutrition, Lucky Charms was a score of 70 out of 100 for nutrition, while an egg was a score of 30?
That's insane.
Yeah, Lucky Charms was better for you. That was the one that was released under Biden, in case you're wondering. The new one is a little wonky in places, but overall nutritionally makes sense. It's that flipped food pyramid.
That's literally South Park.
Yeah. Oh yeah. South Park actually comments on it quite often. Yeah. So, anyways, the new one makes sense overall. God, that one 4 years ago was just get your Lucky Charms because that's healthy. And the one before that wasn't much better. So we had the pie before that, and then the one before that was the food pyramid. And the food pyramid was basically as bad or worse. Yeah. Whatever. Okay, so when we use this system here, we're going to go to the carboxylic acid on our fatty acid, and I'll show you that in a second. And we're going to go the exact opposite side of the fatty acid. And then what we do is we number from that opposite side, and that's going to be the number for the omega. So you may have heard like omega-9 fatty acid or omega-3 fatty acid. That's the number, okay? Now, the polyunsaturated fatty acids like linoleic and linolenic, alpha-linolenic, are going to be considered your essential fatty acids. Does anybody know why they're essential? They're essential because you can't make them in your own body. Okay? There is essentially no essential carbohydrates, by the way, because you can make all the carbohydrates you need in your own body. Okay? So the amount of carbohydrates you actually need in your diet is essentially zero. Right? Now, is that a fun diet to have, and are you likely to succeed in it? Probably not. It's actually pretty tough to do that. Okay? But it is a diet that is doable. And apparently has some uses for like autoimmune diseases, which is quite weird and interesting. But so again, these are going to be compounds that our bodies just can't produce, and so we have to get them in our diet. It's the only source we can get them. This right here is going to be some of the different fatty acids we're going to talk about. These ones with the little stars, the asterisk next to them. Those are essential fatty acids. Now, does it mean you need like huge amount from now on? You need to eat soybeans, safflower, and corn every meal? No. You do actually need to get vitamin C at least once a day, which is a common feeling of college students, which is why you guys are the leading population of scurvy, like pirates used to have. So, army matey. It's a disease that causes your gums to bleed and your spine to bend. Yeah, and you can actually eventually have like wounds that don't heal and die.
But what's it talking
So it's actually from a infection. But when you don't have vitamin C, you very easily catch the infection. Yeah. And so if you keep a decent amount of vitamin C in your body, eat like a fruit every couple days, ideally a fruit every day, you won't catch it. It'd be incredibly rare to catch it.
for college student?
Yeah, so when college students get away from their parents for the first time, they tend to just start eating like pizza and French fries all every meal, and or like one deal of meat if they're an athlete, and nothing else essentially, and just for the protein. And then they don't get any vitamin C for weeks on end, and they catch scurvy pretty easy, and they start bleeding from their gums. That's the big indicator. Okay. That's like your early indicator that you could catch it and actually do something. Otherwise, you probably going to end up with curvature of your spine. So, yeah, they're except for places that literally you just can't get fruit in the United States, they're by far and away the leading population of scurvy. Only major population that gets scurvy, actually. Homeless people do not actually usually get scurvy. Because actually, like, homeless people can get food fairly easily. It's not that difficult to get food.
Does this apply to like vegetables too?
Yeah, okay, so some things that are considered vegetables do have vitamin C. For like me, I really like peppers. And so red and orange peppers have very high levels of vitamin C. So it's never a problem for me. I eat a lot of peppers. Despite the fact I don't get a lot of fruit. So not a particular fan of most of the fruits. Yeah. Okay. So this right here is going to be, for example, this is actually the fatty acid that's in butter, okay, which is palmitoleic fatty acid. And this right here is your carboxylic acid portion right here, okay? And so if we go to the exact opposite end right here, we count off 1, 2, 3, 4, 5, 6, 7. And so that is an omega-7 fatty acid. Again, you got to be independently funny from the 6, 7, okay? Or else it's just sad. So you guys have to be independently funny to use the 6, 7, okay?
Would you say like the line that's in like the middle for each of the ones? Would that be like the one?
This one right here?
Like above.
What do you mean?
No, like you see like the bottom line. The one above it.
Yes, this is the double bond.
Okay.
Yep. This is double bond right here. That's the double bonds as well. Okay, these are all cis double bonds. See how the carbons on both sides are on the same side? Okay. In nature, trans fatty acids, which would be on the opposite sides, essentially just don't happen. I don't want to say they don't happen at all, because there could be some circumstance I'm not aware, but as far as I'm aware, they do not happen. Okay. Now, why do trans fatty acids show up in our diet now? Okay. Not really. It's actually older. It's actually kind of weird history. So what happens is the major source of trans fatty acids is plant oils, have most of your unsaturated fatty acids. Okay. And so when you take a plant oil and you do something called hydrogenate it, hydrogenation is where you take hydrogens and you're trying to get it so it's a saturated fatty acid. So you're trying to get rid of all of the double bonds. Okay. But that reaction does not always go to completion. It actually goes backwards. So when you break it to the single bonds, it freely rotates, right? And so it can rearrange. Instead of being on the same side, it rotates so it's opposite sides. And then if you remake the double bond, it traps it in the trans configuration. Okay? And so you'll see that the trans fatty acids tend to happen in things like peanut butter. They tend to happen in things like margarine. Okay? Where it's a plant oil that we have hydrogenated, so that has a higher melting point. Okay? And that's where you get most of your trans fatty acids. Funny enough, nutrition is so weird and inconsistent, and the best nutritionists, almost exclusively through the history of nutrition, end up blackballed from their profession and literally can't get a job. Like, almost exclusively. In the 1970s, the 14 best nutritionists ended up in basements. They couldn't get a grant. They were completely blacklisted. And that was the food pyramid. Happened because they said we're going to do the food pyramid so they could get people to buy corn. And corn products, right? High fructose products. And they destroyed these 14 nutritionist careers that said, no, that's going to create a generation of who has terrible health. They weren't as diplomatic, though. You can imagine what they said. So one of the weirdest things is, so McDonald's used to use beef tallow for their French fries, which is one of the most healthy ways you can do French fries. And people boycotted them and protested and made them start using trans fatty acids because of terrible nutritional advice, right? And then they've actually repeatedly, this has happened 3 times in the last 50 years, where McDonald's used the healthier thing, and then people boycotted them and made them use the less healthy thing. So it is just like absolute insanity when you look at the history of nutrition.
Do you
Okay?
know the specific reason why they boycotted?
Literally because they thought the less healthy thing was healthier. It's the worst nutritionists are the most sure of themselves and are the ones that get all the money, all the publication, all the fame, and tell everybody how they should live their lives. And it is just freaking psychotic.
It's like that one joke made a few classes hydrogen, something like that.
Yeah. Yep. I mean, it really is. Like, most people don't know enough about science to really know, and they're not going to read the journals, right? And so whoever's confident sounding basically wins the argument, even if they don't know anything. Yeah. And most people that actually know stuff don't sound that confident. They know that they might be wrong. So, yeah. Okay, so let's go ahead and talk about enantiomers now and stereoisomers, more about stereoisomers, okay? So we can have 3-dimensional arrangements that end up around a single carbon, okay? And these are going to be things like chiral molecules and more specifically enantiomers, right? So these right here are actually enantiomers of each other. You can see the only difference here, see this hydrogen is pointing out towards you here? Okay, and the carbon is pointing away from you, isn't it? Over here, it's the reverse, isn't it? That's the only difference. It's just the reverse of those. Okay? And so this is actually limonene. That's the smell and flavoring that you get from like oranges and lemons. Okay? And any product that smells like those. They put limonene in it. This right here is actually limonene that's from turpentine. So that's the smell of turpentine. They smell quite differently, don't they? If you've ever smelled them. Okay? Like you very much would not go, oh, that smells like a lemon. You'd be, oh my God, that's strong. And again, we can distinguish them in our noses because they have different shapes. Okay? That bottom part is oriented the reverse. Right? Everything else is connected the same way, isn't it? Okay. So these right here are enantiomers of each other. They exhibit what is called chirality, okay, or they are chiral. Now, what is chirality and what are enantiomers? So identical molecules are superimposable. Two limiting structures are not going to be superimposable. So these are going to be mirror images of each other that are non-superimposable. Note that you all have examples of this on you right now. Exactly. So chirality literally refers to handedness. And so your hands are chiral to each other. My hands here are mirror images, right? But if I try to superimpose them, what do you see? They're not superimposable, are they? They're not actually the same, despite the fact that they're mirror images of each other, right? They're non-superimposable. Your shoes are also this way. Your gloves, if you have, right and left-handed gloves, are the same thing. All of those things are the same. They're all chiral. When we talk about chirality is kind of like an action that's being taken, whereas the enantiomers are the specific things that are chiral to each other. Okay? So these compounds that are going to be chiral to each other, they're going to be enantiomers. Okay? So we have two enantiomers that are chiral to each other. Right? Okay. And so again, chiral actually refers to the Greek chair, meaning hand. That's the root word of that. And so again, it's going to be the handedness. Most enantiomers are going to contain a chiral center. That's the most common type of enantiomer. A chiral center is going to be a single atom, typically a tetrahedral carbon atom, where you have 4 different things around it. The fact that it has 4 different things means that it will end up being a chiral center. Okay? And you can kind of see this from different objects around you. So if you look at like my cup here, it can never be chiral, can it? Because if we have a mirror image, it just can be rotated right back around, can it? And that's because it doesn't have 4 different things around it, right? It has 2 sides that are same, doesn't it? Okay? Same thing happens to carbons. If you have 2 things that are the same, or you don't have 4 different things around it, it just can't be chiral. It doesn't have enough stuff. If we have our hands, we have 5 different things around it, don't we? At least. So they're very chiral. Okay? Most biological substances and biological systems are highly chiral. Okay? Basically, everything's chiral. Okay, lots of enantiomers. Now, let's identify chiral molecules and chiral carbons in a molecule. So step 1 is going to be locating any tetrahedral carbons. So tetrahedral carbons are ones with 4 different groups around them, right? So a tetrahedral carbon is going to have 4 things around it, okay? Now, that doesn't automatically mean it's chiral because it could have like 2 hydrogens, right? If 2 of those are the same group, then it can't be chiral. So 2 or more of the same group can't be chiral. You're going to inspect that tetrahedral carbon. If you have 4 different groups that are attached around it, that's going to be chiral. If any 2 of those groups are the same, it can't be chiral. Okay? Now, keep in mind that you do have to look at the stuff that's bonded to those atoms that are bonded to carbon. Like just because you have 4 carbons around it doesn't really mean anything. One could be an ethyl and be 2 carbons. One could be a methyl and 1 carbon, right? One could be a propyl and 3 carbons, and those would be different, wouldn't they? Okay. So number 3 is we're going to assign the chiral centers. Typically, an asterisk is going to be drawn next to a chiral carbon, and that'll be a designation. Hey, this is a chiral carbon. One of the things I want to point out is tetrahedral. You may not have caught that when I said that. What are examples of things that are not tetrahedral carbons? Well, that would be things like a carbon with a double bond on it, right? A carbon with a double bond can't be chiral, okay? Because it only ever has 3 things around it, doesn't it? Okay, let's talk about some of the consequences of chirality. So your biological receptors are almost exclusively chiral. I can't think of any biological receptor that's not chiral. And so they're going to be handed. They're going to be give different responses depending on the chirality of the molecules. Okay, and so they're only going to accept and accommodate one unique shape to trigger. So in pharmaceuticals, only a single enantiomer is going to have biological activity for many pharmaceuticals. Has anybody went to the health store and they're doing like a workout routine or trying to get a specific supplement? And you'll see in the health store there's like a D or an L, right? And usually those are smaller containers and they cost more. And then you have one that says either racemic or D and L. Okay, has both an L and a D on it. And those have both both enantiomers. Okay, the ones that just says D or L, one of those only, those are a single enantiomer. Okay, and they've selectively only given you a single one of those enantiomers. And the reason they're more expensive for the amount is because your body doesn't even use the other enantiomer. So when you buy that big container that says DL, half of that container is useless junk that you're just going to pass through you. Okay? No, it's not going to do anything for you. It's only half of it that's actually the active enantiomer, right? And so you're not actually getting a deal oftentimes on those. In fact, you're usually getting a bad deal. Mm-hmm. It kind of depends on the compound, but typically L. But again, it does depend on the compound, and there are a few compounds where both enantiomers will do stuff. Sometimes the other enantiomer does stuff you do not want done. Okay, and we're going to talk about that with this case right here. I always have trouble after I've been lecturing for a while, so excuse me, I'm going to probably get this one tongue tangled. This is going to be thalidomide, and this is where one enantiomer of this actually alleviates the symptoms of morning sickness. Sounds like a really nice drug to take when you're pregnant, right? One little problem, when they first actually created this drug, they didn't really know about enantiomers. And so the other enantiomer of this is tetragenic, and that meaning it causes birth defects. Yeah, everybody looks horrified. Yes, it is exactly what you think it is. It is horrific in every sense of the word. And so this drug was originally sold as a 50-50 mixture between those two enantiomers. So you would take it, it would alleviate the morning sickness, and then it would also cause really serious birth defects in your children, but you would not know that until they were born, right? And so people started having tons of births with birth defects for several years. And finally, they traced it back to this drug and were like, oh my God, what is going on? And of course, they would not have tested this on a pregnant person, right? Like, who would take a pregnant woman and test drugs on them? That would be horrifying, right? Nobody's going to allow that. Unfortunately, this is the sort of stuff that happens. So this right here is a less extreme, more fun example that we're going to do next. Yes, this was just horrific, okay? They finally figured it out. They do actually make the only one enantiomer form of the drug, okay? And so you can get the morning sickness only. Because technically you could also buy the other one, but nobody does. Thank God. I forget the exact date, but like 1950-ish. Yeah, it wasn't as long ago as you'd think.
On the market for?
As far as I remember, you might want to look it up because it's been a while since I looked at the information. But I remember it being something like 3 years. Yeah. Yes. Yeah. I mean, 3 years was a pretty long time, multiple year, but like they would have never been able to trace it faster than multiple year time because it takes 9 months. So S-carvone and R-carvone. This is a fun example, okay? S-carvone is spearmint, and so the flavoring and smell of spearmint, that's S-carvone, okay? Has anybody ever had a caraway seed? They're really common in like bagels and breads and stuff. No? They put them in rice a lot too, in like Mediterranean cultures. Anyways. If you have had caraway seed, awesome. You know what I'm talking about. If you haven't, make a field trip. Get some caraway seed, try it out. It tastes absolutely nothing. It smells absolutely nothing like spearmint. Okay? Absolutely, you would never connect them in your mind at all. Okay? Nothing like. And that is our carva. So that's just the other enantiomer of carva. It's just completely different, right? This is the Thalamin enantiomers. This one's the morning sickness. This is the birth defects. And the only difference here is just this group right here. See, it's flipped. Yeah, most definitely. Of course. Okay. There are actually a ton more examples of this. I'm just going to stop here, but if you start looking into this more and more, you would see a truly tremendous number of examples, ranging from kind of horrifying, where it's literally, there are examples where like one is a popular seasoning and the other is a poison, to like benign and fun ones where they're just different smells and different seasonings. Okay. The enantiomers of your drugs, the enantiomers that you're getting, very much matter on a just monumental scale. The kind of funny example is like methamphetamine meth, the drug, right? That one actually, there's enantiomers of meth that have different times in history have not been illegal because they are not bioactive. And so there actually are cases where people made meth to try to sell it, and then they screwed up. They made the wrong one, the wrong enantiomer. It wasn't bioactive. And so they did not actually get charged for distributing meth. They got, nowadays they charge you for intent, but back in the day they didn't even have an intent law. They just didn't have it. Yeah. So you can actually get really weird cases there. Yeah. Enantiomers. Fun but strange and kind of horrifying.
It was on the market for like about 45 years. So just a little bit more than 3. Like close to
45
5.
years,
No,
really?
sorry, 425. Like,
45. Okay, yeah.
Like
Yeah.
45 years.
Oh wow, it was even longer.
No, that would have wiped out.
Yeah. Yeah. Well, hopefully not everybody would have used.
Yeah.
Would have wiped out most of North America, though. Which would not have been good.